Welcome to the Solutions Part 3 Screencast for Chem 1B at Shasta College. In the previous screencast, we looked at vapor pressure of a solution, and we saw that adding a solute to a solvent made the vapor pressure decrease. Vapor pressure lowering is a colligative property. But that depended upon the solute being non-volatile. And what if the solute isn't non-volatile? What if it's a volatile solute? Well, then both the solute and the solvent have vapor pressures because both are able to form gas. And so we have a vapor pressure due to one of the substances, let's call it the solute, but it now exerts a vapor pressure, so the blue molecules. And the other substance, let's call it the solvent, but that also exerts a vapor pressure, the red molecules. And so the vapor pressure of the solution is going to depend upon both substances, and the relationship is shown here. The total vapor pressure of the solution is equal to the vapor pressure of the solute in the solution and the vapor pressure of the solvent in the solution. And the vapor pressure of the solute in the solution is the vapor pressure of the pure solute times its mole fraction. The vapor pressure of the solvent in the solution is the vapor pressure of the pure solvent times its mole fraction. So note that this is vapor pressure of solute in solution. This is vapor pressure of pure solute. Similarly, vapor pressure of solvent in solution, vapor pressure of pure solvent. And you may want to put a little symbol to note that this is pure and this is mixture, because it's easy to get them mixed up otherwise. Okay, so here's an example of this, example 8. What's the vapor pressure of a solution that contains 50 grams of acetone, which is C3H6O, and 50 grams of ethyl acetate, which is C4H8O2, both at 30 degrees, and we are given the vapor pressure of acetone and the vapor pressure of ethyl acetate at 30 degrees Celsius, so these would be for the pure substances. And so what's going to happen is, because acetone is a volatile substance, it's going to exert some vapor pressure that's going to depend upon the proportion of acetone in the mixture. And then similarly, ethyl acetate is going to exert some vapor pressure that'll depend upon its proportion in the mixture. And of course, both of these will depend upon the vapor pressure of the pure substance at that temperature. Acetone has a much higher vapor pressure than ethyl acetate at this temperature, so we'd expect it to contribute more on a proportional basis, especially since we're dealing with, well, equal grams of each substance. We'll have to see what that is in the basis of moles. So, what do we do to solve this problem? Both are volatile, so we have to use the equation where we deal with the vapor pressure of both substances, and the vapor pressure due to acetone will be the vapor pressure of pure acetone times its mole fraction. Vapor pressure due to ethyl acetate will be the vapor pressure of ethyl acetate due to its mole fraction. Of course, what this means is we need to get both of our quantities in moles. So a fairly straightforward calculation shows that we have 0.861 moles of acetone and 0.568 moles of ethyl acetate. You should probably check to make sure you get the same numbers. And then when we plug into the equation, the vapor pressure of pure acetone at 30 degrees is 285 torr, given in the problem. The moles of acetone is 0.861, and the total moles is 0.861 plus 0.568, which adds up to 1.429 total moles, so that ratio is the mole fraction due to acetone. Then the vapor pressure of ethyl acetate is 118 torr, that's pure ethyl acetate at 30 degrees Celsius, given in the problem. And then with the mole fraction of ethyl acetate is 0.568 moles of ethyl acetate, divided by the total number, 1.42 moles. And when we plug everything in and punch the numbers out in our calculator, we get about 219 torr for the vapor pressure of the solution. And if you think about it, that probably makes some sense in that if it was pure acetone, the vapor pressure would be 285 torr. If it was pure ethyl acetate, vapor pressure would be 118 torr. We'd expect the vapor pressure of the solution to be somewhere between those two extremes, and it's going to be weighted a little more heavily towards the acetone side of things because there's a higher mole fraction of acetone, so it's closer to the 285 than it is to the 118. Okay, now the last colligative property, we've seen freezing point depression, boiling point elevation, and vapor pressure lowering. And the last colligative property we'll deal with is what happens when we have a solvent move through a semi-permeable membrane, and that is called osmosis. And you've probably heard of osmosis before. Worth noting that a semi-permeable membrane is a membrane that typically what it does is it allows the passage of solvent molecules, maybe small molecules, but not solute molecules. So here's a picture. The representation of the semi-permeable membrane is kind of like a fence with holes in it or a barrier with holes in it. Typically that's not really what they look like, but it's a good enough representation for us now. And a way to think of it is water molecules in this case are small enough to go either direction through the membrane, the barrier, semi-permeable membrane, but solute molecules are too big to fit through, and so what ends up happening is we have a net flow of solvent in one direction, and the direction is going to be from high concentration of solvent to low concentration of solvent, or if you prefer, into the more concentrated solution in terms of solute. So you can look at it either way or both ways, but you do have to be careful between solute, solvent, and keep straight which is which. Now, what ends up happening if we have pure solvent and a solution on different sides of a semi-permeable membrane is the solvent will flow into the solution, which is less concentrated in solvent and more concentrated in solute, and the osmosis will continue, and note the net flow of solvent in this case is to the right. And what's going to happen then is in this U-tube, the solvent side will get smaller or lower, and the solution side will get higher. And what's then going to happen is the solution, because it's higher in the U-tube, is going to exert a pressure, and that pressure is going to resist further flow of pure solvent or further net flow of pure solvent into the solution. And at some point, this pressure, which we call osmotic pressure, is enough to stop the net flow. We won't typically have equal concentrations because we still have pure solvent over here and the solution's getting more dilute over here, but the solution concentrations or the concentration gets closer. And so anyhow, the net effect is that the amount of pressure that we need to stop movement, net movement of solvent and end up having equilibrium is called osmotic pressure. And osmotic pressure is given by the following equation. So here's kind of representation. Osmosis, we have a net flow of solvent this direction, resisted by osmotic pressure. At some point, the osmotic pressure is enough to resist further flow, net flow of solvent. We represent osmotic pressure by the symbol pi, Greek letter for P or pressure. No, it's not 3.14159 pi. And then pi is equal to mRTI, where m is molarity of the solute in the solution on the side over here. R is the gas constant. We'll typically use it in liter atmospheres per mole Kelvin, but you'll have to use whatever units are appropriate depending on what's given in the problem. T is temperature, of course, has to be in Kelvin, and I is the good old Van 't Hoff factor we keep on seeing. And note that molarity is moles of solute per liter of solution, so we can sometimes write the equation this way as well, replacing big M by N over V for moles of solute over volume of solution. So either way would be fine. And here is an example of osmosis without a calculation. Maybe some of you have made a pickle before, And how you make a pickle is you start with a cucumber. The cell walls of the cucumber, the exterior, is more or less a semi-permeable membrane. You soak the cucumber in a very concentrated salt solution, and there could be vinegar and other things in there as well. The cucumber has some salt in it, but much, much less. So higher concentration of salt on the outside of the pickle in the solution it's surrounded by, which means net flow of water outside of the cucumber outward from the cucumber. And what ends up happening is the pickle becomes salty because some salt does get into it, but the cucumber shrinks, if you will, as it makes the pickle. And then just as a side note, there's a link on your handout, actually 2 links. There is a pickle-related song done by the old folk singer Arlo Guthrie, the motorcycle song it's called. And then I don't think that's that great a song, kind of funny, but he's also well known for Alice's Restaurant, so there's a link to that on the handout as well if anybody wants to go down a rabbit hole of good old 1960s folk music. It's a pretty good song. Long, though. Okay, so cucumber forms pickle, and that's an example of osmosis. More will be done in class. Okay, so for the last thing in this screencast, we have a problem that deals with determining osmotic pressure, so a practice calculation with regard to that. So example 9, what is the osmotic pressure of normal IV saline solution at 25 degrees Celsius? Normal IV saline is what you would get at a hospital for rehydration, and we are given that normal saline is 0.90%. The W/V here stands for weight to volume, so that's another type of concentration unit that can be used, and so it's 0.90% weight to volume of NaCl. So we would like to find osmotic pressure, and what we know is osmotic pressure is molarity times gas constant times temperature times Van 't Hoff factor. Or we could also write it as moles per liter, moles of solute per liter of solution, times gas constant times temperature times Van 't Hoff factor. So gas constant, we've seen before, we just look it up or remember it, 0.08206 liter atmospheres per mole Kelvin. Temperature has to be in Kelvin, so we'll have to add the 273 to 25. For NaCl, NaCl breaks apart into 2 pieces, so I is 2. And then the problem really hinges upon getting the concentration, either in units of molarity or getting the moles and getting the liters, from the concentration given in a different set of units. So basically what we need to do is to note that 0.90 weight volume percent means that if we had 100 milliliters of solution, we would have 0.9 grams of NaCl. So 0.9 grams of NaCl in 100 milliliters of solution. Percent means out of 100, so we have 0.9 on the basis of grams, out of 100 on the basis of volume in milliliters. And so basically what we're going to have to do then is to convert the grams into moles and the volume, milliliters, into liters. And that should be fairly straightforward to do. So let's do our calculation here. Number of moles, 0.9 grams, works out to be 0.0154 moles of NaCl. You might want to double check you get the same number as I do. 100 milliliters, of course, is 0.1 liters. R is 0.08206 liter atmospheres per mole Kelvin. 25 degrees Celsius is 298 Kelvin. And then I, of course, is 2. And notice moles cancels moles, Kelvin cancels Kelvin, liters cancels liters. We're left with atmospheres, and 0.0154 times 0.08206 times 298 times 2 divided by 0.100 works out to be 7.53 ATMs, and we were carrying some extra digits in the intermediate calculation, so we started with 2 sig figs, so we should probably round our answer off to 2 sig figs. So osmotic pressure of a 0.90 weight to volume percent normal saline solution is 7.5 atmospheres.